Okay, so in this discussion, we're going to talk about some basics about linear regression. So suppose we have data x, which is n by p dimension, which means we have n observations and then p columns. We are interested in the model of x multiplied by beta, and then with some error term, we're going to hope that it equal to our predicted value. We want to find a set of a beta that could make that happen. So our predicted value for each of the observation, it's a scalar, and then our predictor has our coefficient to be estimated is a dimension of n by 1, p by 1, and then we have a n by 1 epsilon term, or the error term. We're also going to impose the error term with a mean of a zero vector, constants variance for each of the observation, n by n dimension here for identity. Okay, so let's first comment on the distribution for y. Y here is basically a linear transformation for our random variable epsilon, which also have a normal. So we basically just shifting away by the amount of x beta from 0. So our random variable y, which inherit the normal from epsilon, has the new mean equal to x beta. We do not perform any scaling here, so our variance stay the same. So x beta, they're all considered as fixed at the moment. The only random variable is the epsilon. So our y here, which is a linear transformation of a normal random variable, also has a normal distribution with the mean is equal to the parts that we shift away from the mean of the original random variable, so x beta. Same standard deviation or variance here. Okay, so that would be the setting here. Now we are interested in estimating the beta. Let's denote as a beta hat. We are going to find the beta by performing an optimization problem, by solving an optimization problem. Here, denote y minus x beta as the error or the residual from our predicted value from the true value. And then we also need to take the square. This is the equivalent of a scalar version for each of the observation multiplied by the beta coefficient taking the square. They are the same, except that I'm using the matrix vector multiplication or this kind of a notation for this discussion. Okay, so now let's work on solving the optimization problem. We first expanding the terms on the right hand side. Y transpose y minus 2 copies of y transpose x beta. So y transpose x beta, we have 2 copies of that, minus or a plus beta transpose x. So this is a transpose of that. So beta transpose x multiplied by beta from here. Denote that as our objective function or loss function, L of beta. Beta is our variable or parameter of interest. Taking the derivative with respect to beta for this loss function, we have 0, nothing to do with beta, and then 2 copy of x transpose y. Here I'm changing the order just to make sure that we are matching the dimension here. I want to make sure that the gradient here is also a p by 1 vector. So I have a p by n by 1. So it has a p by 1 dimension, just to matching the dimension here. Also plus x transpose x multiplied by beta. So let's see. P by N, N by P, or this is a P by P matrix, P by 1. Okay, P by 1. So it should be P by 1 as well. And we are just going to match with this particular dimension here. Okay, maybe let me just erase that. Set the gradient equal to 0, solve for beta. So X transpose Y equal to X transpose X multiplied by beta. Our beta hat is equal to X transpose X inverse. So left multiply here, X transpose Y. We have our closed form solution for our beta hat that is obtained by minimizing this objective function. Okay. Next, let's talk about some or the distribution for beta hat. Denote this as a matrix A. So you can see that basically your beta hat is a linear transformation to another random variable that follow a normal distribution. So that tells us that our beta hat should also follow a normal distribution at least. But the question now is, what will be the expectation or the mean and the variance for our beta hat? So now let's evaluate this expectation by plugging our solution, our closed form solution for beta hat. This part only involving the data or the parts that is not random variable. There's a typo here. This is not beta, this is Y. Transpose Y, closing the expectation. Denote this as A. So the A here only involving X, which is data. So we can bring that outside the expectation. Okay, expectation of Y, that's what we have earlier from here. Mean of the random variable Y. So let's plug in X transpose X inverse X transpose multiplied by X transpose beta. This is equal to beta because this X transpose X inverse cancel out with left multiplied by this X transpose X. We only have beta. So you know that the beta hat is a normal distribution centered around the true variable beta, or the true beta here. Okay, next let's talk about the variance for X transpose X inverse X transpose Y. Okay, again, consider this as A. So we should have something like variance or A transpose variance of Y, A multiplied by variance of Y multiplied by A transpose. This is just a rule for a linear transformation of a random variable. And then you can write in that. And now let's plug in A here. X transpose X inverse X transpose. Variance of Y is just sigma identity N coming from here. Okay, coming back, we have A transpose. So A transpose is the X transpose of a transpose. And then X transpose X inverse, and then the transpose. And this is a symmetric matrix, so the transpose is just itself. Okay, so we have that. Let's further simplify. Sigma squared is a scalar in the front. X transpose X inverse X transpose. Continue from here. X and then X transpose X inverse. These two cancel out, or either one if you want, equal to sigma square x transpose x inverse. Okay, so that should conclude our discussion on the distribution of x beta hat, on the beta hat. So beta hat follow a normal distribution centered around beta with this particular variance covariance matrix. Okay, so now we are going to look at this problem from another perspective. So we are going to circle back to here. Here we solve the beta coefficient or the estimation from minimizing the residual or sum of square residual. From this perspective, we get the solution for beta hat here. Next, we are going to solve this question in the MLE perspective, maximizing the log likelihood. So let's denote our PDF for variable y, so which is a normal distribution, but we're going to write it as a multivariate normal, dimension n over for n. So this is a n by 1 vector. So we have a n-dimensional multivariate normal. And determinant of sigma matrix 1/2. And then, so this should be the 1/2 of the determinant of the sigma matrix. And the sigma matrix here is actually, so let me just make a side note here. It's essentially here, this matrix n by n, but I'm just going to use the sigma for this matrix here as a general notation. But in our case, in our setup, it's equal to a sigma multiplied by that, also an n by n matrix. I'm just going to use the sigma matrix as our notation for now. 1/2 y minus the mean. So mean is x transpose x beta. And then inverse of the sigma matrix, x minus beta. So this is just a formulation or for a multivariate normal, and then the dimension here is just the n. Okay, now let's define our log likelihood, and it's a function of our parameter beta. So taking the log, we have that. Okay, so here I'm just going to use the log for natural log. So in statistics, usually people use log, but it doesn't matter which base. It just we are usually using log for natural log. Minus 1/2 log determinant of sigma minus 1/2 y minus x beta transpose sigma inverse y minus x beta. Okay, so this is just the log likelihood of and then it's a function of beta. Next, we are going to take the derivative with respect to beta again from the log likelihood function. So no longer the objective function by minimizing the sum of square residual, but this is the likelihood function. So 0 minus 0. These two things has nothing to do with beta. And let's see, minus for now 1/2. Okay, so now we need to take the chain rule. So we have 2 copies of that, so we need to multiply by a 2. And also, maybe I'll just keep this part here. So sigma inverse y minus x beta multiplied by x, the one that associated with beta. So there's another chain rule. Here, if we want, maybe we can't match the dimension. This is n by p. Okay, so if you want, maybe write this as x transpose here. So let's see, this is a p by n, n by n, n by 1. We should have a p by 1 here just to match. And yeah, maybe I'll just, so the 1/2 and square. Don't forget there's another minus sign here. So it's a plus. Set it equal to 0. Okay. So we just need to, if you want to be rigorous, just pay attention to the dimension. But yeah. Okay. So let's see. What else we can do here? Maybe I'll bring in the the identity matrix here. So we should have x transpose y and 1 over sigma square for this. Yeah, so that is just 1 sigma square identity. So now I'm going to plug in this to replace the sigma matrix. Equal to x transpose x beta. Don't forget there's another copy of that. Let me clean this up. So yeah, I'm just going to replace this here. So there's also a 1 over sigma square for the x transpose x beta. So I'm jumping a few steps here. I'm just first rewrite that as 1 over sigma identity, and then x transpose y, and then x transpose x beta, and then move it on the right hand side to the of the equal sign. So we have that. And this is similar to what we see earlier. Beta hat is equal to x transpose x inverse. Move it left, multiply this, and then also canceling the 1 over theta. 1 over sigma. Okay, so as you can see, when we estimate the coefficient of the beta from a maximum likelihood estimation perspective, we obtain the same closed form solution as we solve this problem from the minimizing the least square. Okay, so what we have seen so far is that we see 2 ways to solve the x beta, and we also comment on the distribution for x beta. well, no, for the beta hat. Okay, maybe next we can find the estimation for sigma square. So let's borrow the notation from here. Now we are interested on solving the sigma square. So usually the sigma square is also unknown, so we should estimate them. We should estimate it from data as well. So let me just copy down here 1/2 log determinant sigma matrix. I think here maybe we can just maybe if we plug in now, it will ease the computation. 1/2 let's see, 1 over sigma square y minus beta transpose y minus beta. Okay, so let me just double check. Here I'm plugging sigma identity, and here because we have an inverse, so I need an inverse. Okay, now let's work on this, on solving the sigma. Maybe we can also further simplify that. So this is log of sigma square raised to the power of n when we move it outside the determinant, and then determinant of identity n. And the determinant of our identity is just the product of the diagonal elements. So it's all 1. So this becomes a 1. Okay? And 1/2 sigma square, 1/2, an inverse y transpose x beta transpose y minus x transpose. Okay, now I think we are, maybe let's make one more transformation. Log of something raised to the power of n is equal to n multiplied by log of that. So we have another copy of that. So I bring the n from the power into the numerator of the fraction. Now let's take the derivative with respect to sigma square, which is a scalar. Okay. Zero plus minus sigma square, 1 over that, plus 1/2. So bring the minus sign here, sigma square -2. Okay, set it equal to 0. So we have 1/2 sigma square -2. Here I'm just going to use E to denote y minus x transpose x, so residual. So This E is different from the epsilon. This is just defined as y minus x beta. And also, if you want to be, so you might also want to refer this as the difference between the true the difference between the true and the predicted value. So you want to plug in the beta hat here to refer this is the residual here. Okay, so that's just a definition or a notational thing. Because we're just working on that and working on one of the variables, so we need to plug in the one that we estimated earlier to solve for the other one. Otherwise this is still like a two unknown two equation problem. So here we have one of them and we solve for the other one. Okay, bring this part to the right hand side. Sigma square that, and let's see. We have E transpose E and copy sigma square. Okay, so what I did here, first remove the 1/2 from both sides. Also multiplying sigma square raised to the power of 2 on both sides. So this cancel out and we only have one more copy here. Sigma square hat is equal to E transpose E over N. Okay. So you can estimate your variance for the model that we set up here from the data. And this is under lots of assumption here. First of all, is constant variance for each of the n observation, and error term follow a normal distribution, and these things proceeds. So everything is still within what we specify. Okay, so maybe for the last part of this video, I want to talk about the expectation. Oh, so maybe I'll just use, just to mention one more thing, this is also under the MLE framework because we are maximizing the log likelihood. But just to comment on that, yeah. So the last thing I want to mention, talk about is the expectation of that. Let's plug in E transpose E over N. 1 over N is a constant, so E transpose E. Here, let's make some more comments. Earlier we defined the residual is the true value minus the predicted. Here, let's also define another matrix H. This is X multiplied by X transpose X inverse X. This is what we call a hat matrix, so we use H here. And this should have a dimension of let's see, n by p, p by p, p by n, so n by n dimension. The hat matrix is referring to when we multiply by the true value, this is actually the prediction. This is because this is beta, x multiplied by beta, hat, the prediction. And this is x multiplied by x transpose x inverse x transpose y. And we call this part as H, and this is the same as when we multiply the true value, we are adding a hat. So we call this the hat matrix. And it's coming from x multiplied by beta. And we plug in the beta, so this is beta hat, the one that we predict. Learn from the data, plug in here. So that's another thing we introduce here. Now, continue our definition for beta hat minus y hat, y minus h multiplied by y equal to identity minus hat matrix multiplied by y. Okay, so I minus h, n by n, n by n, n by 1. Okay, just to comment on that, we define residual as I minus h. Okay, one more comment. I minus h, it's symmetric. Also, I minus h, it's idempotent. So I multiplied by I minus I multiplied by h minus I multiplied by h plus h multiplied by h. And now I just left this part for you to verify. H multiplied by h is just h. I minus h, I multiplied by h is also h. Minus one copy, minus another copy, plus another copy of h. I minus h. So, idempotent. Okay. Here are just the side notes that we want to make. Now back to our original question. 1 over n. Y multiplied by I minus h. Let's see. Okay, so this should also work, but let's not yet finishing this. Let's see, where should I bring it here? Okay, so let's continue from the definition. This is the error term as we have specified here. Okay, and it's also equal to 1 minus h epsilon. The reason for that is, let's see if I can. This y is the true value, so it's coming from the model. Okay, so maybe let me use the proof to finish that the second line. I multiplied by x beta plus that minus x transpose x inverse x transpose x beta minus h epsilon. Let's see. Okay. Okay, we have x beta plus epsilon minus cancel out x beta minus h epsilon, and these two cancel out. 1 copy of epsilon minus h multiplied by epsilon. So it's equal to that. So just to summarize, residual defined as I minus h multiplied by y is also equal to I minus h multiplied by epsilon. Okay, so instead of using y, maybe I'll use epsilon. The reason is that epsilon follow normal, mean, zero, sigma, identity, dimension n. This is the n by 1. Okay, so I think I'll use this part to replace the residual e here. Okay, so all the right hand side are side notes, and let's back to here. So we are going to use that definition. Epsilon transpose I minus h transpose. Then I minus h multiplied by epsilon. Okay, so here we're going to use the things that we defined that we commented earlier. I minus h is symmetric. You can verify that by yourself when you well, h is symmetric, I is also symmetric, so it's symmetric. Also, so after it's symmetric, so we can remove the transpose here. Also, it's idempotent altogether. Maybe let me just write it here. So this is a 1 by n after transpose, n by n and n by 1. So this thing essentially it's a scalar. One thing we can play around when we see a scalar and expectation is by adding the trace. Closing the expectation. Trace of scalar, it's scalar. So scalar is equal to trace of scalar. So that's why we are adding a trace operation here. Next, the cyclic rule for trace operation. Move this to the end. So epsilon, epsilon transpose. Closing the trace, closing the expectation. You can only perform this transferring the order by the cyclic way. So the first one to the end, and then this will become the first, and then this one to the end. So you have this. If you want, you can have that move to the end. But we are just going to work on that. Okay, next. Linear trace and expectation, they are all linear operation. So we are able to change the order. Okay, I is a constant. H only composed of X. It's a data, also constant. So they can move it outside the expectation. I minus H expectation of epsilon, epsilon transpose. So this is a n by n matrix now. Okay, what else we can do? Now we need to work on this. So, side notes again. Here, let's define a sigma matrix as the variance-covariance matrix for epsilon. Okay, so this is referring to the epsilon, the variance-covariance matrix for epsilon, which we know is actually the sigma identity. That's by our model assumption. Here we just comment on one thing. This is equal to the expectation of, let's see what notation to use. Maybe I'll just use a general notation to, okay, and then in the end we'll just make the switch. Okay, so how about this? So let's write here, variance-covariance matrix of your random variable y, and this is the mean vector for the random variable y. This is just a general case. Later we will refer this y as actually epsilon, and this is all the covariance matrix of epsilon and the mean vector of the epsilon. But here just referring to general form. Okay. y transpose minus 2y transpose mu. Okay. Okay, so maybe, yes, okay. So this is actually y and mu transpose. So this is the y multiplied by mu transpose, and I'm also going to use this here. So there are 2 copies of that, plus mu transpose. Okay, so later we'll rewrite y as sigma. So here you can see that this is already this part that we are interested. So I'll change that to epsilon later. E of y multiplied by mu transpose plus mu transpose. Okay, so we have, let's see what else we can write. Then y transpose is sigma plus mu transpose. So I'm going to move this. So this has only 1 copy left, and then I move it to the left hand side. So it's sigma plus 1 copy of that. And if this is the epsilon, then this is just the sigma square identity, dimension n plus 0 column vector multiplied by 0 column vector, so it's just 0. So the expectation of epsilon transpose is the variance covariance matrix for the epsilon. Okay. Once we have that, come back to here. Identity n. Okay, so we should have sigma squared, it's a scalar outside. Trace of I minus h only. Because identity multiplied by that is just identity. This is a scalar. And then we can move it outside the trace. So the question is, what is the trace for that? If you want, you can here I'm just trying to be more, not to skip some of the steps. Trace of identity should be n, right? Sum of the diagonal elements, n of ones. So they're all n by n and n by n. minus trace of x transpose x inverse x transpose. So we can change the order x to the n due to the cyclic rule for the trace, and we will have a trace of identity. Yes, but okay. So here I want to point out this is the identity matrix with dimension p, no n, because x transpose x inverse x transpose x. So here I'm referring to the trace after I bring the x to the n. X is a n by p matrix, so this is a p by n multiplied by n by p. P by n multiplied by n by p. So as you can see, this is a matrix of identity dimension of p. This one is a dimension of n, but after we change the order here, this is a dimension of p. So we have n minus p over n sigma squared. And as you can see, this is not an unbiased estimator. So E sigma hat is not equal to the true value. And if you want to make it a unbiased estimator, you need to use this. So you need to multiply by the inverse of that for the estimator, so that it will cancel out with this when you evaluate the expectation. And that will equal the true value. That will be the unbiased estimator. You need to multiply by a factor of that. Yeah, so in this video, we covered some basics of a linear regression model. And we comment on the distribution for beta, and we also calculate the expectation. We first solve or find a closed form solution for sigma hat, and we solve for the expectation for that, and we see this is not an unbiased estimate. You need to multiply by a factor to correct or to adjust that. Okay, so I will stop here.